Good afternoon, everyone. My name is Yufang Li from the Hong Kong University of Science and Technology, Guangzhou. Today, I'm excited to present our work on GPUnion autonomous GPU sharing on campus. This project aims to address the significant challenge of GPU resource utilization in academic environments. Let's start by looking at the problems. In academic settings, we face a GPU dilemma. We see a pronounced imbalance. Some labs have abundant GPU clusters while others struggle with minimum capacity. This leads to significant temporal underutilization, as even well-equipped labs experience idle periods. Furthermore, diverse research often requires a variety of GPU architectures from consumer-grade to high-end, creating heterogeneous needs. All this contributes to accessibility barriers for students and early-stage researchers. Our ideal vision is to democratize access to these vital computing resources. We want to improve overall GPU utilization, reduce hardware waste, foster collaboration, and ultimately lower the cost of innovation for a broader academic community. However, existing solutions struggle to achieve this vision. Traditional infrastructure as a service platforms like OpenStack are simply too complex and resource-intensive for voluntary campus environments. They are built for traditional VM orchestration, not dynamic GPU sharing. Even modern container orchestration platforms like Kubernetes, despite supporting GPU scheduling, fundamentally rely on a centralized control model. This clashes with the voluntary nature of academic resource ownership. They treat node volatility as a failure, whereas in a campus setting, resources come and go frequently. Furthermore, Kubernetes introduced significant operational overhead that often exceeds the expertise available on campus. And while voluntary computing projects like City Homes share some similarities, they operate in untrusted wide area networks with coarse gain tasks, and their focus is on user incentives, not empowering resources providers, which is crucial for us. So, how do we address these limitations? We propose GPUnion, a campus-scale GPU sharing platform built on three core design principles. First, autonomous participation. Unlike data centers, campus resources are decentralized. We adopt a provider-first paradigm, giving resource owner absolute control, including a kill switch to reclaim resource instantly. Second, lightweight and transparent usage. We want GPUnion to be frictionless. For users, submitting a job should feel no more complex than running it locally. For providers, hosting workloads shouldn't require complex reconfiguration. We achieve this through containerization for seamless encapsulation and minimal overhead. Finally, reliability, resilience, and security. Given the dynamic nature of participation, our system must be robust. We ensure user workloads remain resilient through automatic checkpoint and migration, and enforce strict sandboxing with container isolation, guaranteeing security despite fluctuating resource availability. Let's dive into the architecture of GPUnion, which is designed with these principles in mind. As shown in the figure, the system is comprised of several key components. The central scheduler and coordinator acts as the coordination hub, managing resource discovery, allocation, and workloads across campus. It's designed to handle dynamic resource volatility, unlike traditional schedulers. Each participating node runs a lightweight provider engine. This engine is crucial for provider supremacy, exporting local control mechanics and enabling the immediate kill switch functionality without coordination overhead. This also performs real-time monitor of GPU metrics. All GPU workloads execute within a containerized execution environment using Docker containers and the NVIDIA Container Toolkit. This provides near-native GPU performance with strong isolation across diverse hardware. Finally, we had distributed state management and monitoring for real-time telemetry, and a flexible data storage architecture that supports both centralized and distributed storage, allowing users to specify data location. We deployed GPUnion in a real campus network environment involving 11 GPU servers with a mixed architectures from RTX 3090 to A100. After a 6-week period, we observed significant improvements. As shown in figure in the left, the average GPU utilization across all servers increased from 34% to 67%. This was largely due to enhanced visibility and automatic allocation of opportunistic workloads. Furthermore, interactive debugging sessions increased by 40% as students could more conveniently access idle GPUs. Our resilience mechanics also proved highly effective. As detailed in figure in the right, we achieved 94 successful workload migration during rescheduled provider departures. Even with frequent interruptions, the impact on total training time was minimal, showing only a 3 to 7% increase compared to uninterrupted execution. Crucially, the network overhead for checkpoint and migration was negligible, consuming less than 2% of available campus bandwidth during peak periods. This work opens several exciting venues for future research. We can explore heterogeneous large model deployment, developing new approaches for model partitioning and load balancing across diverse GPU architectures. We also aim for user transparent resource invocation by integrating AI-powered resource estimation and scheduling, making it even easier for users. Finally, we will investigate scalability for large deployment, potentially through hierarchical coordination or gossip-based decentralization to extend GPUnion beyond mid-sized campus environments. Thanks for all the support. That's all. Thank you.